So this problem is a two-part problem. First part is to draw the first derivative of this graph. I'm given a function. Say this is my y of t. This is my time axes. This is some, say, position graph. And it's going to tell me what the position of an object is at any given moment. And it asks to draw the first derivative. What is the derivative of this? Derivative, if you remember, is nothing more than how fast this function changes at any given point. So this actually is, as we go through this problem, this is going to be nothing more than figuring out what is the slope, the instantaneous slope at every one of these points. I'm going to draw a couple points in here just to kind of divide up our region into a couple regions so we remember what we're doing. There's a second part of this problem that's going to ask us for the second derivative. So we'll use these same positions to show us some interesting values. So I'm going to switch to blue, and we're going to draw the first derivative. We're going to draw y prime. Well, I'm going to actually start in this region. This region down at the bottom is pretty easy to do. We'll see that it's flat. If we were to think about it of a person, they start at some point, they move backwards. This is time. So as time goes forwards, they move to a position more negative. And then in this region between these two dotted lines, they don't move. They're always at the same position for a certain amount of time. Maybe they're here for 2 minutes, and they're sitting at some negative value. So if they're not moving, then the derivative of this, which is known as the velocity for a position versus time graph, the derivative of it is going to be 0. Mathematically speaking, this is the slope of the line. So if I were to look at this point here, I'd have a slope of 0. So my slope equals 0 in this position. I can jump over this region over here, and I'll see that I get the same slope equals 0. All my lines over here are all flat. The position is not moving. It's not getting larger. It's not getting smaller. So there is no slope for this point in the line. So the slope is 0. And when we draw the slope of 0, when we draw the derivative, we're drawing the value of the slope, 0 there. This region in the middle right here, well, it looks like it's a straight line, but it has some slope. But we'll see that the slope here, the slope there, the slope there, all of these slopes are the same value. They're a positive value, so I'm just going to say it's at some positive value up here. But what we get is that it's a positive constant value. The slope doesn't change, so the value of the slope doesn't change. And we know that there's a little curve at the end where it goes from 0 slope to positive slope, so that means I have to connect these 2 points. It's a continuous function. And we go from a positive slope back to a 0, so this thing has to go back to 0 there. So we stay at a 0 position, or at a constant position. Then we jump up with some velocity. We're moving at constant velocity, which means that we constantly are getting further and further away from our starting point. And then we go back to a constant velocity. Let's look at the very beginning of this. It starts off with a slope of 0. So that means it starts off at the origin for the value of that slope. The derivative is 0. We're doing the y prime of t. Well, as we go through this, the slope of this is going to get steeper and steeper and steeper. This slope right here is steeper. This one is actually even steeper. It's more and more negative. So if I were to draw the slope of this line, it's going to be some negative value. It looks like a parabola to me, so the derivative of a parabola is a straight line. And I get to some point over here. At this dotted point, this is my steepest point in this graph. At this point, it's actually going to start to go more positive. So in this case, we know it goes back to 0 slope over here. So it looks like it does a turnaround and goes back around. So we start at some value, get an ever-increasing negative velocity. We turn around, go back down to 0 velocity. We sit at some position because we're at constant velocity of 0 until we hit this point here. At this point, we start to move towards the positive direction, which means we have a positive velocity. We're moving at a constant rate because this is a constant slope, so we get a constant velocity until we hit this last point where we slow down to 0 velocity, down to 0 velocity here, and sit at this point again. So this is what the derivative, the blue is the derivative of our graph. Now, if we wanted to go through and figure out what the second derivative was doing, it's a little bit of a tricky thing to do. Just because we're going to need the first derivative to help us out. So I'm going to fold the piece of paper I just got done working with, and we're going to try to do the two things together. So I get my first derivative looked like this. I'm going to draw my second derivative now. First thing I'm going to do is I'm going to label those points again that I had as reference. And the last point was somewhere over there. Okay. So now we're going to, and I'm going to do this in red this time. So y double prime of t. This is going to be my acceleration. If I'm doing a position versus time graph for my original, I'm going to try to plot the acceleration, or how fast am I changing my velocity. So the second derivative is nothing more than the derivative of the first derivative. The second derivative, we just take the derivative again. So I'm going to look, this is a constant value here, so I get another constant value right there. Over here, up here, this slope is 0 again. This line is not increasing or decreasing. The derivative is not increasing or decreasing. So that means the second derivative is 0. There is a region in the middle where it goes from some value up to another value. There's a rising area right here that we're going to have to take care of. We're going to just skip it for right now, move on to the last region. We're at 0, constant 0 in our derivative, which means our second derivative is a constant 0. So I'm getting a lot of 0 accelerations. However, we said that this point right here, we go from some velocity of 0 to some constant velocity. That means in order to go from 0 velocity to some positive value velocity, we had to have some acceleration. So the acceleration is going to go up, and then it has to go back down. So it's going to get an increasing slope. It's going to go to a very fast increasing slope, and then it's going to go back to a 0 slope. So 0, fast increasing, back down to 0. Same thing here. It starts at some velocity, constant velocity, and then it's going to get slower, which means that its acceleration goes negative and comes back to 0. When we get to this region in here, we're at a constant 0 velocity. The constant velocity part means that we have no acceleration. Back over in these regions, we got to look at this, and we're going to see that we have, in this region right here, over in this area, we go from some value to some other value. It looks like it's a straight line. It has some constant slope, and it's a positive slope. So I can look at this, and I see that there's a positive slope there. It looks to be a pretty constant value. Again, it connects through, but there's a constant value. Over in this area, we have a constant negative slope. It's not as steep as this region over here, so I'm going to make it a little bit less steep, but it looks like it's a constant slope all the way from the beginning. So that means it's going to be some constant value up until we get too close to the dotted line, at where it goes from some negative value, some negative slope to positive slope, which means we have to go from a negative value to a positive value in our second derivative. So this is what the acceleration looks like. It looks like we're getting some force or some acceleration in the negative direction. This causes our velocity to speed up and causes us to move in the backwards direction. We hit this area right here where we start to slow down because we have to go to a zero speed, which means we sit at the same position. So our negative acceleration goes back up and we go back to zero. The area of this part right here and the area of that part should be identical areas in order for this to work out right. We sit at zero acceleration with zero velocity, so we're sitting at some constant position. We now spike our acceleration. We give ourselves a quick little acceleration area, which causes our velocity to go from zero to some constant value. And at some constant value, we're going to move in the positive direction and step off certain amounts of distance every time. We get to the end. We're going to go back to a constant velocity. We're going to sit at that position, so constant velocity of zero, which means we have to do a negative acceleration. Negative acceleration, this will slow us down from some positive velocity. We do a negative acceleration, and we get back down to zero acceleration, where we are finally at zero velocity, and we maintain zero velocity. So we maintain that constant position at the very end along this top part. So this is what the derivative and the second derivative of this function looks like.